Okay, so the goal of this video is to analyze and be able to create a slope field. And a slope field really is just a visual representation of the behavior of the function, the behavior of the graph, based on just its slope. And so the idea of like here, example one, here's someone's derivative, dy dx equals 2x. So I want to just analyze, well, what does this look like if I measure this slope at all of what I'm going to call lattice points? And when you see the word lattice points, what it just referring to is just any spot like on the coordinate system that have integer values like 0, 0, 0, 1, 0, 2, -1, 1, -1, 2. And so these little dots or these points on the graph are going to be my lattice point. So this point right here is the integer value 0, 0. This one here would be like 1, 0. This here is like 2, 0. So I'm just going to analyze this particular derivative, or what I call a differential equation, and it's just an equation that has a derivative in it, by analyzing the slope. And so right now my dy dx is equal to 2x, a pretty simple function. Every derivative is equal to 2x. So if I wanted to evaluate the slope at the point 0, 0, I really just have to rely on the x component. It's a 0. So I'm going to put 0 into 2x. I'm going to put it in right where the x is. 2 times 0 is 0. So I know at that instant the slope is 0. So what I want to do is represent that. What does that look like? What does a slope of 0 look like? So a slope of 0 is a horizontal tangent line. So I'm just going to put like a dash. Oops, sorry. Thought I selected blue. I'll try one more time. So I'm going to put a dash to represent a slope of 0. And then I'm going to go to the next point, 1, 0. And if I, again, just think about 1, 0 and put just the x value, because that's what the derivative says is 2 times x. 2 times 1 is 2. So I want to draw something that looks like it has a slope of 2. So it's kind of just my estimate, but it's going to be uphill, and something that might look like that, a slope of 2. And then let's go to the next point, 2, 0. Well, 2, again, putting it into the x, 2 times 2 is 4. So it's going to be a steeper slope than 2. And again, it's just my perspective. It's just a little dash that's going in that direction. And then finally, at 3, 0, I'm really interested just in the x value of 3. 2 times 3 is 6. So I'm going to have a very steep slope of 6. So again, my slope value was 0, and then it went, and I'll maybe highlight this since you can't see what I'm pointing at. It was 0, and then it was 2, and then it was 4, and then it was 6. So I'm just trying to capture the steepness of the slope at that instant. So I'm going to fill in all of these points. But yeah, and I know what you're thinking. This is tedious, right? There's a lot to do, but there is some pattern. Like the fact that there's only an x here means that these don't depend on the y. So going back to the initial point 0, 0. Well, the point here where x is 0 and y is 1, it's still going to have a slope of 0 because its x value is still 0. So I can put a horizontal line there to represent a slope of 0. At 0, 2, its x value is 0. At 0, 3, its x value is 0. And in this particular differential equation, it's just the x that's going to affect the slope. Down at 0, -1 has a slope of 0. 0, -2 would have a slope of 0. 0, -3 would have a slope of 0. So it can kind of be a bit efficient. And same thing along the next column of lattice points. 1, 0. Well, it's 1 times 2 is 2. This is 1, 1, but it's still a slope of 2 because it's just the x value. This has the same x value, 1, 2, 1, 3. They all, in this example, they all have the same x value, so they all would have the same slope, 2 times 1 to get a slope of 2. This next column would have a slope of 4. So I'm going to mimic, okay, this is a slope of 2. So a little steeper, a slope of 4. A little steeper, a slope of 4. A little steeper, a slope of 4. And it's not perfect. It's just a trend or a direction. And then something even steeper, kind of getting cut off there. Something even steeper than the slope before would be a slope of 6 here. So then a slope of 6, slope of 6, slope of 6. Same thing down here. And again, I can go this quickly because in this example, all of the x's are the same along the column. Now, if I go to this point here, -1, comma 0, comma 0, now its x value is -1. And when I put that into the differential equation, 2 times -1, we'll have a slope of -2. So now we're going downhill. And then this point is -1, comma 1, but its x value is still -1. -1 times 2 is -2. This also becomes -2. This also becomes -2. So each of these slopes will become -2. And then I move to the next column. Each of these x values are -2. So like -2, comma 0. I'm going to focus on that x of -2 and put it into the differential equation. -2 times 2. Now it's a slope of -4. So a little bit steeper. And we're really just kind of mirroring the slopes on the other side, just in negative direction. And each one should try to be consistently the same steepness, but it is, it's just a sketch. It's not going to be perfect. But when you're finished, you should be able to kind of like pull away from the image or kind of take a look and say, oh, like there's a little bit of like, I see trends, I see movement, I see a shape kind of emerging. And the shape that I hope you see is something that looks like a parabola, something that's quadratic, right? Something that, kind of starts to go down and kind of taper off and come back up, right? It has sort of this parabolic shape. And it's sort of, it's really just, it's centered along the y-axis. It just, it just kind of, the slopes increase as you, move away from the origin. And that's exactly what should happen, right? If you think about like, why are we getting this shape? Why does it have this shape? It's because think about the derivative that we started with. Our differential equation was dy dx was equal to 2x. Some derivative is equal to 2x. Well, I know a function who has that derivative, right? Think about that. What function would have a derivative of 2x? I could use the antiderivative, the integral of 2x, if I really wanted to, dx, and that would equal, x squared plus c. So everything should have that quadratic, right, x squared shape plus c. Maybe it's x squared plus 2. Maybe it's x squared plus 3. Maybe it's x squared plus 4. And what this slope field shows are basically all the possible families of functions. Sorry, I'm trying to pick up my cursor. I guess I can't, sorry. But what it's showing is all possible families of functions, x squared plus c. So they all have the same shape. They're all parabolas. It's just that their intercept will be different depending on what your constant is. Okay? So that's our first differential equation. Okay. Now, we can draw another slope field for example 2. And it says this particular one is determined just on the y variable. I'm going to square the y. So I'll start it off, and I won't have the whole video go through it. What I'll do is then I'll pause it, and I'll create the next video where it's already done. Because once you understand, all you're doing is plugging in the point. You don't need me to do each point. You're just doing the y value. So I'll do the first couple. So here's 0, 0, right? So 0, 0 squared. So again, it's just the y value this time. So 0 squared is 0. And this point, which is 1, comma 0, also has 0 as its y value. So its slope is 0. And the next point, 2, comma 0, has a slope that's 0. So that, or has a y value that's 0. So its slope would be 0. And then this one is 0. So all of these along this line that I'm drawing, because their y value is 0, it's going to have a slope of 0. So I'm going to draw just a horizontal segment there. And then let's go up to the next row. This is 0, comma 1. So at this point, because its y value is 1, I'm going to show a slope of 1. And this also has a y value as its component. So that'll be a 1. And then this will be a 1. And this will be a 1. Because again, each of these lattice points has a slope value that's equal to 1. And so again, it's my interpretation of what a slope of 1 would look like. Okay? So take a second here. and fill out the rest of this slope field. And again, because of this particular differential equation, it's just dependent on the y value. And I'll go ahead and stop this video. And then on the next video in the sequence, it'll be done, and we'll kind of talk about what does it mean to draw a particular solution through -1, 1.